Hey there, physical science students. This is Miss Ruark. We're in podcast 2.3, and we're going to finish up with Newton's third law. All right, so far we've talked about the first and second law, and in the first law we said it was the law of inertia, which means that if something's at rest, it stays in rest, or if something's in motion, it stays in motion until an external force acts upon it. We just did a great lab where we got to play with inertia, and we were pulling the cloth out from underneath the table, the glass dishes. It was a lot of fun, right? Okay, and then the second law talks about it talks about an unbalance of forces. So in the first law we have a balance of forces, and then on the second law there's an unbalance of forces, and that unbalance of forces will cause something to slow down or change its motion. And so now we're into the third law, and the third law deals with action and reaction. But before we get there, we do want to talk about this force that holds us on this earth, and it's called gravity. Okay, so gravity is a force that's on earth. It's the pull of an object on another object. So it's not just earth. We have gravity that we exert onto other objects and other things. The only thing is, it's so small in comparison to the Earth's gravitational pull that we don't notice it. Okay, so the paper clip that is on a piece of paper that you get from your teacher, it has gravity, but it's not as big as the gravity that you feel from the Earth, and therefore you don't notice it. All right, if we're near the Earth's surface, let's try that again, and we are in free fall, and so we have a free fall change in motion. That would be because of gravity. So that would be if we're, skydiving. Hey, everybody likes to skydive, right? Or if you go bungee jumping and you're falling, that would be the free fall, change in motion. Okay, so that is the pull of gravity, or the free fall. You accelerate until you get to 9.8 meters per second squared. That's the pull of gravity pulling you down towards the Earth. So you accelerate, you change your motion, you change your motion, you're speeding up until you eventually can't speed up anymore, and then you hit terminal velocity, which means that you can't speed up any faster. You are in free fall. There's no way you can go any faster. All right, weight versus mass. Now, a lot of people confuse these two. There is a difference. Okay, mass is the amount of matter that an object has. Okay, so if we were to take the mass of something in class, we would try to figure out what its mass is in grams. It is going to be the amount of matter that an object has. It will not change unless the object itself changes. It doesn't depend on gravity. Okay, on the other hand, weight, that's going to be a measure of gravity pulling on that mass. Okay, it does depend on gravitational force, and it's going to be measured in newtons. Okay, so if we're on Earth, and it says it here, if we're on Earth and you're a person who weighs about 140 pounds, your mass, let's say, is about 63.5 kilograms. So your weight is going to be 623 newtons. Well, if we went to the moon has less gravity to it. So your mass is still the same. It does not change. Your weight now is 103 newtons. You're only 23 pounds. That was a really nice diet, wasn't it? Okay, but then you go to Jupiter. If you've heard anything about Jupiter, it is extremely massive. It's very big. It's got a lot of mass to it, and the things that have more mass are going to have more of a gravitational pull to them. So it has a really big gravity on it. Okay, so your mass doesn't change, but now your weight is 1,582 newtons. So you weigh about 355 pounds. Yeah, it's pretty big. All right, well, what if we went to the sun? Let's hypothetically speak that we could go to the sun. We won't burn up. Okay, your mass stays the same. The weight of your body, of your person with gravity pulling on it, because the sun is so big and has so much mass, its pull of gravity is so much bigger. So your weight on the sun would be about 17,418 newtons, which will be about 3,914 pounds. That's huge, right? And you're just a normal sized person here on Earth. Okay, so gravity pulls on matter, and that's what gives us our weight. Mass stays the same no matter what. All right, law of universal gravitation. All objects in the universe attract each other through gravity. We just talked about that. The larger the mass, the larger the gravity. Smaller the mass, the smaller the gravity. So a paperclip is going to have an extremely small gravity compared to let's even say a car. Or a car is going to have an extremely small gravity compared to the moon. And the moon, being so much smaller than the Earth, has a smaller gravity than the Earth. Well, the Earth, it rotates around the sun, right? Orbits around the sun. So the sun must have an even bigger gravity. So if you increase the mass, you increase the gravity. If you decrease the mass, you decrease the gravity. All right, well, can we take that mass that has such a hard gravity and make it weaker? Well, we can if we increase the distance between those two objects. Okay, so let's say that we had object A here and object B here. Okay, they're so close that the gravitational pull between those two will be pretty strong. It'll increase. What if I take those and I split them out and we make A here and we put B all the way over here? Do you think they're going to be able to feel the pull, the gravitational pull between the two of them that they would feel if they were this close? And the answer is no. As you increase this distance here between them, the gravity, the pull, is going to weaken. It's going to get less. Okay, if gravity is the only force that's working on something, like you jump out of a plane, well, gravity is the only force that's working on you there, so it would be considered free fall. All right, so getting into this third law. The third law talks about action and reaction. It says for every action force, there's an equal and opposite reaction force. Okay, so what does that mean? Well, if you push on a wall, it says that you're pushing on the wall, that's your action force, and then the opposite reaction force would be the wall pushing back on you. All right, so here's an example. Here you have a person who's getting ready to jump out of a boat. The action is that the person's going to push off of the boat here to propel himself into the water. Okay, the reaction from the boat, the boat is actually pushing on the foot of the person, and the boat will go in the opposite direction. Let's look at another one. All right, here's another one. Here we have a balloon. The balloon's full of air, and as it releases that air, okay, it's releasing that air down and out. Okay, so that's the action, as it's coming down and out. Well, the reaction is that the air molecules are actually pushing the balloon up. So the balloon is going up because the air is going down. Okay, let's say that this person here, you get to deal with my lovely drawings. I'll even put some hair on it. See? Hair on it. It's a girl. Okay, this person here has a soccer ball, and this person kicks that soccer ball. So the action is the force, the foot touching the ball, and the ball's going to go this way, right? Well, the reaction is that the ball is actually pushing off of the foot. Okay, so for every action there is a reaction. All right, and with action and reaction comes momentum. Okay, so what is momentum? It's a quantity defined as the product of mass and velocity. So it's mass times velocity, and that gives you momentum. And they use a little p. Well, they use a lowercase p for it because the lowercase m is already used. Okay, so mass and velocity come together to give you momentum. If it has a bigger mass, it can create more momentums, have a bigger momentum. Okay, so if you had two objects that were different sizes, let's say that we have this bus here and then we have a teeny tiny little car. I already talked about this in class, but we'll talk about it again because it's important. This bus is going to have an extremely large momentum because it has such a large mass. Doesn't matter if it's going slow or not. It's going to take a while for that bus to slow down. Okay, it's going to have momentum. It's going to be moving. All right, well, what if we had some objects? Let's see. Oh, and here, this bullet, okay, this bullet can have a large momentum. It has a small mass, but it has a large momentum because it's moving at a higher velocity. So faster velocity can create more momentum. So even small things can have a large momentum. All right, well, what about something that's not moving? Well, if it's something that's not moving, if the object is at rest, it has no momentum, no matter how large its mass. Okay, remember, it's a product of mass times velocity, and if something's not moving, you're multiplying the mass times 0, so it ends up being 0. All right, momentum can be conserved. Okay, conservation of momentum is when you take the total momentum of all the objects in a collision and you add them all together, and it should be exactly the same as the momentum before the collision. All right, so here are some examples. We'll look at these later. Let's come over here to the balls. Okay. In class the other day, you guys were probably playing with them, And you notice that if you picked up one and you let it drop towards the other ones, it would fall, it would hit all of them, and it actually passes the momentum, like it is here in figure 2, all the way through all of those balls to the one on the outside. And the one on the outside would take off. And then it would come back in, and it would pass the momentum all the way through until it got to the other ones, right? Okay, so total momentum of all of them, even though this has no momentum, and this one, and this one, this one, this one, but this one does have a momentum. So after the collision, and it's now over here, if you add it all up, it's always going to be the same. Okay, conservation of momentum. All right, so here we have an object that's rolling, the orange ball is rolling, and the yellow or the white ball is stationary. When the orange ball hits the stationary ball, the orange ball now sits still, but the white ball takes off, and it has the same amount of momentum that it did before the collision. Okay, total when you add it up. All right, what if we take these two balls and we roll them towards each other, and they smack each other here, and then they both bounce off and they go off in the opposite directions? Okay, well, what happens, you have the total momentum of the orange and the white ball together. It should be the same as the total momentum going opposite of the orange and the white ball. All right, well, what about this one? Here we have the orange ball moving pretty fast, and the white ball's not moving as fast. So the orange ball is going to catch the white one. It's going to catch up, and it's going to smack it. But now there's going to be a transfer of momentum. It's still going to be the same. It's still going to be the total that was here is going to be the total that's here. But now the orange ball is moving slower, and the white ball is moving faster. So it just transferred that momentum. All right, and here's a little gravity lesson from Wile E. Coyote from back in the day, and I'll see you in class.